Assalamualaikum warahmatullahi wabarakatuh. Now we want to present about line integral for vector calculus. Now I want to introduce my team members, which is ATHIRAH NABILAH, ALLYA MAISARAH, and SOFIA.
Now we move on to the introduction of line integral. The definite integral is used to calculate the area under the curve of the region. The line integral extends the definite integral by replacing the straight line intervals of integration with a smooth curved path in two-dimensional or three-dimensional space. Katz in 1981 describes the development of the line integral concept. In the early 19th century, Augustin Louis Cauchy studied integrals along curves and developed results that resemble modern line integral. Additionally, the theorem of line integral was further defined with advanced method in the 20th century by Josiah Willard Gibbs and Oliver Heaviside. Now we move on to the theorem 1. If C is the graph in two space or three-day spaces of a smooth vector valued function Rt, then its arc length shown in the slide, which is L equal to integration of A to B with the magnitude of the Rt. Next, we move to the theorem 3, which is the work done, with W equal to integration of F times dr equal to integration of A to B FRT times R prime T. Integrate with respect to dt. Now, the last theorem, which is theorem 2, it is the same thing, but it only differentiate with between, which is 2D space and 3D spaces. So for 2D, integration of f as y plus g as y with respect to s equal to integration of f as y with respect to s plus integration of g as y with respect to s, which is ds equal to third of dx over dt to the power of 2 plus dy over dt to the power of 2. So last but not least is the application of line integral. Line integral are used in several cases. Firstly, it is used to find the length or mass of a wire. Other than that, it can also help to find the conservative fields if the line integral along closed loop is equal to 0. It depends on the initial and end point of the path. However, some of the criteria need to be met to evaluate the line integral. The evaluation formula for both scalar and vector line integrals are strictly applicable under the condition that the integration pathway is a piecewise smooth curve across a closed interval. In addition, if the function of vector fields contain discontinuities, singularities, or undefined points along the path, the integral may fail to exist or require special treatment using improper integral technique.
I will start with question 9. Let T be a curve represented by function r equals sec3 plus sin 3d, where t is less than 0 or more than y. So to solve equation Roman y, integrate c y over 2s squared ds. So first, we have to know where is function r. After that, we have to differentiate for r prime. Then, we have to find the magnitude of r prime, where is here we got 3 cos 3t. Then, we substitute into the integrate c y over 2s squared ds, where we get integral 0 1 sin 3t over 2 times sec 3 squared times 3 cos 3t dt. Then our final answer we will get 1 over equative for Roman tool integrate of the FDR, where fxy equal to y squared over x squared plus y squared irradiate power of 3 and y squared. First, we have to come up with fxy. We have to know x is sec 3 and y is sin 3e. And then, we have to find r prime, where is r prime equal to 0 and 3 cos 3t. We substitute into f of dr. We get 3 over 3 times sin squared 3e in bracket of 3 times sin squared 3e in bracket times with r prime, where is 0 and 3 cos 3e. we get the answer 3 sin square 3t cos 3t dt. And when integrate, we have to use Lexio substitution where u equal to sin 3t, du equal to 3 cos t, 3t dt. After we are substituting into u, we get 2 patients uy, u square du. The grade we got u of 3 over 3. Our last answer, we substitute again a value of u. We get sin power of 3 over 3. For members over, I just take for xy, then differentiate of t, well, is to find ts, and then the answer can save as a manual calculation. For 2, I use for declare fy and differentiate for fy, and the answer will also for the same as our manual calculation.
Today we are looking at a classic vector calculus problem. We want to find 2 things. First, the line integral of vector field f along a straight line segment C. Second, we want to find the actual arc length of this curve C. The line start at coordinates 1, 1, 4 and end at 2, 2. Let's see how we solve this step by step. To solve this manually, we start by parameterizing the line segment. Using the parameter t from 0 to 1, we get our position vector rt and its derivative rt. For the line integral, we substitute our x, y and z equation into the vector field f. After simple integration, we get an exact answer of 26.5. For the arc length, we integrate the magnitude of derivative of rt, which is give us a clean value of exactly 3. Finally, we can verify our manual math using Mapper Solver. By loading the vector calculus package and define our parameter equation, we calculate the line integral and speed. As you can see, Mapper complete match our manual calculation. The arc length is 3 and the final integral answer is 50 over 2 or 26.5. This confirms our manual step as 100% correct.